Hi, my name is Jim Gleason. I'm the husband of longtime Green Hills Middle School teacher Chris Gleason, who is now retired from Green Hills but continues to work as an educational consultant. I'm a retired electrical engineer and I'm the volunteer developer of the Green Hills Renewable Energy Dashboard that we call the GRED. Chris was the driving force behind the GRED development. The GRED performs continuous collection, display, and archiving of performance data from Green Hills rooftop renewable energy assets as a resource for student education. It also collects data from a rooftop weather station. Electrical power from the rooftop wind turbine and the solar array, data from the rooftop weather station, and temperature measurements from the green roof and the standard white roof that covers the majority of the school are routed into the GRED display cabinet inside the school. Power from the wind turbine and the solar array is stored in a 12-volt battery inside the display cabinet. The battery is connected to two 5-watt LEDs that illuminate the display wall located next to the cabinet. The display cabinet allows students to see all of the hardware that goes into the GRED control and data acquisition process. The laptop computer in the cabinet controls the entire process, archives the data, and updates the real-time high-definition TV display. The poster boards document the entire process. Green Hills is making GRED data, documentation, and other related resources available for the benefit of teachers and students at other schools through the public website whose location is listed here. The GRED data is directly available at this location. A reference documentation file is available here. This video, available from the public website, will augment the information contained in the reference documentation file. I'm going to step through all the slides in the reference document, but I'm not going to read all the information on each. The viewer can pause the video to read all of the information on the slide, or can go directly to the reference document itself. Another video, also available from the public website, we'll discuss some example GRED data plots that show many of the basic characteristics of the data. I hope that this video and the one just mentioned will help teachers to overcome the learning curve associated with becoming familiar with any new source of data, and that they will then be able to formulate some plans as to how to use the GRED data for the benefit of their students. Teachers are welcome to modify the reference documentation file and share it with their students. Comments, questions, or suggestions are encouraged and can be addressed to me at my email address listed here. This slide provides some basic information on the wind turbine, the solar array, and the green roof. The wind turbine and the solar array do not produce very much electrical power. They are not tied into the school electrical grid. Instead, they are dedicated entirely to student education. The green roof, on the other hand, does have practical utility for insulating parts of the school and also controlling the amount and temperature of water runoff. The GRED data is derived from sensor measurements. One of the rooftop temperature sensors is pinned to the white roof, shown here. The thermistor is located at the very tip of the temperature sensor. The other rooftop temperature sensor is tucked underneath the green roof. The weather station produces several environmental measurements. The GRED cabinet contains 3 voltage sensors and 4 current sensors that are used to monitor the performance of the wind turbine and the solar array. The process for getting at the GRED data files is shown in the next 4 slides. But instead of talking about the slides, let's go back to the public website directly, and we will put the process in action. This is the GRED public website as it currently exists. We can scroll down to the link that then takes us to the folders that contain the data, the documentation, and the related resources. Left-clicking on the data log shows the archive files that are currently available. The ENV files contain the environmental data that derive from the rooftop temperature measurements and from the weather station measurements. The renewable energy files that begin with RE relate to the wind turbine and the solar array. The ENV daily file contains environmental data averages over whole days. Correspondingly, the RE daily file contains renewable energy averages over whole days. Those two files run back to March of 2015, and they are updated on a daily basis. The ENV and RE hourly files contain data statistics over 1 hour time intervals. These files are separated out by each year. The two hourly files for the current year are updated at the end of each day. We also maintain renewable energy files on a minute-by-minute basis, shown here. The RE Minley files contain data for a specific month. They are updated daily. They go back to March of 2016 as designated by the year and the month number. The example plot video will talk about why this minute-by-minute data is needed. Left-clicking on the display file brings up a screenshot of the real-time display that is provided above the GRED cabinet at Green Hills. The display at Green Hills is updated every second, but this file in the archive is only updated on an hour-by-hour basis. We'll return to the information shown here later during this video. All of the archive data files are saved as tab-delimited spreadsheet text files. That's the .txt extension shown here. The spreadsheet text files can be imported by any standard data analysis package, such as Excel or MATLAB or Fathom. Left-clicking on one of these text files allows you to see what's in it, but it shows up as a text file, which is not particularly useful for analysis purposes. But right-clicking on it brings up the little window shown here, and if you select the Save Link As option, it will allow you to download the text file to your local computer, which I will do here, and I will save it, and I'll replace the old one that I have, and it's then saved on my hard drive. So let's import the file, the text file that we just downloaded, into a spreadsheet program. In this case, we'll be using Excel. Importing the data into programs such as MATLAB or Fathom should be very similar. So I've already started Excel, so let's go to File, Open, and it just so happens to be pointing at the location of my downloads, which is where the file actually is. but we don't see anything showing up initially. And the reason for that is because Excel tends to come up looking for Excel files, and a text file is not an Excel file. So we can say all files, and now we see our particular file. So we will double click on it, and it brings up the import wizard. And this is where it's important to know that it's delimited data. There's some other details here that fortunately, typically you can just totally ignore. And we say next, and here it allows us to select what kind of delimitation it is. It's tab, and it shows us that it's looking pretty good as tab data. So we say next, and we finish, and now we have our data available for more detailed analysis in Excel. All of the archive data files begin with a first record that is a set of column names. These are followed by data records. In Excel, we can select an entire spreadsheet, all the data, and we'll just then widen the width of this first column, and it does all of the others. And the only reason for doing that was to expose the full names of the various data columns. And of course, we can scroll across and look at them all. But some of the names are rather long, but they are quite descriptive of what the particular data field is. I'm not an Excel expert, but when I import data, the timestamp typically comes up looking something like this, that is not very useful as a timestamp. So what I do is go up to here where we can select the format. We'll select this particular column, the timestamp column, and we'll go down to more number formats, and one of the choices is custom, and we can then scroll down to minutes, days, years, hours, minutes, month, day, years, hours, minutes, and we say OK, and now the timestamp is much more, looks like. Timestamps represent the start of the data collection interval. So this is our environmental daily file. So this says that this first record begins on the 1st of March 2015 at 0, which is basically just 1 second after midnight. And so it implies then that all of this data represents information collected over this entire day of the 1st of March. As we scroll down, we can see successive days. They're all in here, and we get down to the current last day that went into this particular file was the 24th of February of 2017. Understanding the environmental data should be straightforward. The GRED control software reads the weather station data 20 times per minute, that's every 3 seconds. But it is important to note that the various weather station quantities are updated at varying rates. For example, the wind speed is updated every 3 seconds, but at the far extreme, the solar radiance is only updated every 50 to 60 seconds. Some of the weather or the temperature data in particular is typically updated more on the interval of every 10 seconds. The table provides a useful reference listing of all of the column names. The duration column is the actual time duration of the data acquisition interval. For the ENV daily data, you would expect this number to be close to 24 hours. However, it could be significantly less due to stoppages of the control software during the period of the day. The data is organized as a sequence of columns with average values, followed by an identically ordered sequence of min values and max values. The min and max values for the hourly data represent the extremes over the individual measurements. The min and max values for the daily data represent the extremes over the hourly averages. I'm going to talk about the renewable energy archive files in two parts. The 7 GRED voltage and current sensors provide a complete characterization of the power delivery process from the wind turbine and the solar array, as will be discussed in detail shortly. But before getting to that, I want to talk about a subset of the renewable energy archive data that focuses on the basic capability of a wind turbine and solar array to deliver power for a useful purpose. In the GRED case, that purpose is providing power to the 12-volt battery and the two 5-watt LEDs. It's suspected that teachers looking into the GRED data will find this reduced set of the renewable energy archive data to be very beneficial to their students, without having to fully comprehend the more complete but more complex discussion that followed. The simplified GRED architecture on this slide shows that the DC power from the wind turbine charge controller and the solar array charge controller are delivered in parallel to the 12-volt battery and the two 5-watt LEDs. The two charge controllers are needed to prevent overcharging of the battery. They prevent power backflow, implying that the power from the 12-volt battery can only flow to the LEDs. The LEDs periodically discharge the battery partially. If the LEDs didn't partially discharge the battery, the wind turbine and the solar array would not be able to output any power once the 12-volt battery was fully charged. When the LEDs are turned on, power from the wind turbine and the solar array flows to both the 12-volt battery and to the LEDs. Understanding the renewable energy data is inherently more complex than is the case for the environmental data. The renewable energy data is inherently more complex because it depends on all of the components shown in the block diagram here. The table on this slide lists the subset of the renewable energy archive data files that are specific to the delivery of the wind turbine power and the solar array power from their respective charge controllers to the battery and the LEDs. The LED's on percent is included because the on-off state of the LEDs will have impact on the power output. The wind speed, solar radiance, and outside temperature information from the weather station is included in the archive as a convenience. So let's move on to talk about the full renewable energy archive. This discussion is equally applicable to the data subset that we just talked about. This slide shows the complete GRED architecture. The green boxes are the basic renewable energy components, and the yellow boxes are the components that are required for the data acquisition. Notice in particular the locations and the names of the 7 sensors that are used to characterize the performance of the wind turbine and the solar array. I'm going to briefly show the 2 slides that follow this one and then return to this slide. The wind turbine current to its charge controller is measured on one of the 3 AC input phases. The current on the other 2 phases is not measured, but they should have the same magnitudes, but phase shifted by plus or minus 120 degrees. The wind turbine voltage to its charge controller is measured across one of 3 input phase pairs. The voltages across the other 2 phase pairs are not measured, but again they should have identical magnitudes but phase shifted by plus or minus 120 degrees. The solar array DC voltage to its charge controller is measured. The input current to the solar array charge controller is the same is that flowing out of the charge controller to the battery and the LEDs. The wind turbine charge controller rectifies, that is, converts, the three-phase AC input to DC power output. The wind turbine charge controller output current is measured, as is the current into the LEDs. The current flow through the rechargeable battery can be calculated from the other currents that have been measured. The voltage measurement here is termed the battery voltage, but it applies equally to the battery, the LEDs, and the two charge controllers since they are all wired in parallel. So we have the electrical properties of the architecture completely characterized, assuming that the sensors and the relay do not have any significant effect on the voltages and currents. Further, given voltages and currents throughout the architecture, we can calculate power at any point. This slide provides more information on the renewable energy calculations performed by the GRED control software. It's interesting to note that we start with voltage and current sensor measurements that are obtained at 300 samples per second. I'll show a video in a little bit that illustrates why that high data rate is necessary, at least for some of the sensor measurements. Every second, the GRED control software calculates average or root mean square RMS statistics from the high data rate samples. The 1 second statistics are then averaged over periods of 1 minute, 1 hour, and 1 day, and those are what goes into the archive data. The control software tries to keep the system operating in what we call the automatic mode. The goal is to avoid the situation wherein the wind turbine and/or the solar array power output is limited by their respective charge controllers. When those limits are hit, it indicates that the battery is highly charged, and consequently neither the wind turbine nor the solar array can produce very much output power because there's no place for it to go. Keeping the system operating in the automatic mode and stopping the charge controllers from preventing the flow of power has been a challenge, and it's been hard to achieve it on a consistent basis. Some of the elements on the GRED real-time display are updated every second. Those showing 1 day, 1 week, and 1 year histories are updated at a slower rate. This video of the GRED display was obtained on a very windy day. The red curve up here is the AC voltage output of the wind turbine to its charge controller. The white line is the battery voltage, and the blue line down here shows the output current from the wind turbine charge controller. The wind turbine AC output voltage can reach frequencies approaching 10 Hz, as can the wind turbine output AC current. The 300 sample per second data rate is used to be able to capture those two waveforms. The wind turbine charge controller produces output current when the input voltage peaks exceed the battery voltage. As the wind slows down below speeds of about 10 miles per hour, the voltage peaks drop and the charge controller does not produce any output current. The solar array charge controller will begin to produce power in very low light levels. That amount of power increases to its maximum value of 5 watts as the solar radiance increases. This is an enlargement of the GRED display auto mode monitor. The auto mode monitor tracks the change in the battery energy level over a 3-day period. The zero change point is set when the battery is fairly well charged, but hopefully it is not charged to the point that either of the charge controllers are preventing power flow to the battery and the LEDs. After setting the 0 point, the GRED control software turns on the LEDs via the relay. The LEDs then remain on until the battery energy drops by a designated amount, in this case 20 watt-hours. The LEDs are then turned off, and the battery is then allowed to recharge over time from the combination of the power produced at the output of the two charge controllers from the wind turbine and the solar array. When the battery energy then gets a little bit above the 0 point, the LEDs are turned back on and the discharge cycle begins again. The energy plateaus in the charge cycles represent the case at night where the solar array is producing no energy, and it just so happens that the wind turbine is not producing any energy either. When the GRED control drops out of the automatic mode, which does happen sometimes, the system is then manually set into either a discharge cycle or a charge cycle until the auto mode is reinstated. Here's a listing of all the columns in the RE hourly archive files, a subset of which were listed under the Part A discussion. Hopefully the meaning of each column will be clear from the previous discussions. Note that the wind turbine current and voltage to its charge controller are derived from the 1-second RMS statistics. All of the other data is derived from the 1-second averages. So the wind turbine RMS current to the charge controller hourly average for a full hour represents an average value over 3,600 RMS 1-second statistics, obtained from 300 high data rate samples. It should be noted that several of the current and power statistics are signed, that is plus-minus quantities, that represent both magnitude and direction. For example, for the battery, positive numbers represent current or power flow into the battery, and negative numbers will represent current or power flow out of the battery. Be aware, the GRED data is not perfect. I've uncovered a number of bad data records and removed them, but I'm sure I have not found them all. Some known anomalies are listed here. Some aspects of the data may look like anomalies, but in fact are just the artifacts of doing a real-world data collection. The example plots that I mentioned earlier will show some of the real anomalies and will also show some of the characteristics that appear to be anomalies, but in fact are not. I hope that this documentation video was useful to you, and I hope that you will proceed to watch the example plots video that is also available from the public website.